Okay, you should have completed the first data table, graph, and 3 accompanying questions on page 8. Hopefully we had similar results. Here we go. The relationship between diameter and circumference should have clearly been positive. As the diameter increases, the circumference also increases. And that should be represented pretty clearly by a line on your graph that goes upward and to the right. So we can fill in right here for graphical relationship as positive. Your mathematical model should reflect this by showing both numbers on top as numerators with no denominators because we don't have any other variables to represent right now. So I wrote something that looks like this. C is directly or positively related to D. Circumference is positively related to diameter. One thing to note here is that as diameter increases, by how much does the circumference increase? For example, if the diameter were to double, what would happen to the circumference? Take 30 seconds and discuss this with your partner. I'll repeat the question. If the diameter were to double, what would happen to the circumference? 30 seconds, go. Ten seconds. And time. So assuming that your graph has equal spacing along the axes, it's clear that the graph is linear, meaning that both values increase at the same rate. Both circumference and diameter increase at the same rate. This is reflected in my mathematical model as an exponent of 1. Now, we don't typically write exponents of 1, and so I left it off. If the relationship were not linear, then there would be an exponent other than 1 in my mathematical model. And my graph would reflect this by showing an increasing relationship, but with a shape that is not a straight line. We will see some more examples of this in later units in physics. So finally, I can make a prediction. For me, I made a prediction that looks like this. For every doubling of diameter, circumference will also double. And you could have phrased it differently, like for every tripling of diameter, circumference will also triple. For every half of diameter, the circumference will also half. Whatever happens to diameter, the same thing will happen to circumference. Okay, that should do it for this page. Or for this data table. The next data table and graph on page 8, we will not be using. So go ahead and put a big X through that, and let's move on to page 9. Let's answer those first 2 questions, A and B. A says, what is a mathematical term which refers to the steepness of a line? Let's take about 15 seconds and discuss that question with your partner. 15 seconds, go. And that's your time. Hopefully you've heard of the term slope before. Slope is the mathematical term that refers to the steepness of a line. The larger the slope, the steeper the line. And if you've taken any algebra before, then you may recognize the generic equation for any line as y equals mx plus b, where y is the dependent variable, x is the independent variable, and m is the slope of the line. Have you ever wondered why slope is represented with an M? Well, some experts think it's because the French word for climb is, I'm hoping I pronounced this correctly, monter. Now, some people believe that's where the M in that equation comes from. I'll give you 10 seconds to write this down. Okay, at this point, you're just going to repeat the process that you did before. Only this time you'll be measuring and graphing the masses and volumes of various objects. You will work in table groups this time. That's groups of 3 or 4, depending on how many people are present. You will need a scale, a graduated cylinder, and a pink tub full of various different objects. And you're going to measure the mass and volume of those different objects. Now, before I let you get to it, I don't remember if we've talked about this before, so I'm going to mention it just in case. When measuring the volume of regularly sized objects, meaning objects that have right angle dimensions, we just multiply their width, length, and height. But when measuring irregularly shaped objects, that really isn't an option for us. And so we can still use a graduated cylinder. What we do is we fill the graduated cylinder with a predetermined amount of liquid, and the easiest case would be water. Then we would drop that object into the graduated cylinder and we would observe how that volume changes. If we take the difference between those two volumes, the new volume after we drop the object in and the old volume before we drop the object in, the difference of those two will be the volume of that object. So that's how we measure the volume of irregularly shaped objects. All right, that should do it for instructions. So again, you're just repeating the same process. Once the video ends, go ahead and retrieve your materials and get started.